Today, we want to talk about finding equations of lines, in particular, equations of lines tangent to functions at given points. That was one of the advertised purposes of the derivative. Find the slope of the line tangent to a function at a given point. So, since we've become so skilled in finding derivatives, having 2 whole days of a complete set of derivatives to work on, 12 derivatives must be exhaustive, right? We have everything covered. That should get us well on our way to our 10,000 hours of practice. Oh man, maybe not. We had like 4. All right, we're close. We're close. We're experts. We're experts. So, because we all come from different algebraic traditions, I want to talk about how I like to think of lines and linear functions. So we start with this problem. Find the equation of a line containing the point -2, 3 with the slope of -4/5. I want to look at the function version of the point slope form because I can write this down with this information without having to do any calculations at all, which is what we want. So I write y equals 3 minus 4/5 times the sum of x and 2, which is actually -4/5 times the difference between x and -2. That would be a better way to phrase it. I know it seems like the same thing, but it is super different because the point slope form has x minus x naught. So we're looking at the difference between x and -2. Here's how we want to read what's going on and why I like this form. This form says y is equal to 3. It starts off with where things start, where we're centering our focus on this point -2, 3. Y is 3 when x is -2. So the form of this equation says y is 3, and then we subtract 4/5 a bunch of times. That's what's going on. The x plus 2 says, how many times are we subtracting 4/5? That's the read that we're putting on here. Y is 3 minus 4/5 times x plus 2. So we start at 3. And we subtract 4/5 a bunch of times. We can get away with this because linear functions are very simple things. Linear functions are just a product of repeated addition that we summarize with multiplication. This x plus 2 tells us how many times to subtract 4/5. When x is equal to -2, we're saying start off at 3 and subtract 4/5 0 times. When x is equal to -1, we start off at 3 and subtract 4/5 1 time. When x is equal to, I can't remember where I was, 0, we start off at 3 and we subtract 4/5 2 times. That's the number of times we subtract 4/5, and it works backwards. When x is equal to -4, we start off at 3 and we subtract 4/5 -2 times. So we add 4/5 2 times. This is how linear functions work. It's a process of repeated addition. In this case, that's subtraction, but subtraction is just -1 addition. It's the inverse of addition. So start at 3 and subtract 4/5 a bunch of times. If I was going to build a table of values, y is 3 when x is -2, and we subtract 4/5 a bunch of times. So 3 minus 4/5 is going to be 2 1/5. We subtract 4/5 whenever x increases by 1 every unit. So 2 1/5 minus 4/5 is 2 and negative 3/5. Man, that's not how we say that. How do we say 2 and negative 3/5 normally? We subtract 4/5 a bunch of times. And we can do this backwards as well. If I go to negative 3, that's +1 the other direction. And we'll just have to do this backwards. And that tells us where we need to be. Any questions? I don't know why I thought I would need this much table. So the other thing that I want to point out is that a linear function is an action of repeated addition. Linear functions act with repeated addition. The pattern here in this linear function is repeated addition. And the way we summarize repeated addition is with multiplication. And that's why we multiply over here. This is how I like to think about the mechanics of a linear function. It's an operation that it's a function that has a pattern of repeated addition. Another reason I like to think about linear functions this way is that it makes it very easy to upgrade our linear functions to exponential functions. Linear functions have this pattern of repeated addition that we summarize with multiplication. If we upgrade to an exponential functions have a pattern of repeated multiplication. And we summarize repeated multiplication with exponents. So that's why a pattern of repeated multiplication will give us an exponent, exponential function. So sidebar. Exponential functions have a pattern of repeated multiplication. So for example, here's an example of an exponential function. Y is 20 when x equals 3. I've given you a starting location. Y is 20 when x is equal to 3. And y increases by 8% every unit. I just realized that I was going to use doubling, but I'm like, I'll do 8%. That'll be, and then I realize I need a machine to do 8%. Not the first one, but I'll need need repeated 8%. That's going to be trouble. So what's going on in this function? Y is 20 when x is equal to 3, and y increases by 8%. Now I've got to translate that into multiplication. When things increase by 1%, you're increasing by multiplication. Increases by 8%, we can translate to multiply by 1.08. So we could translate this by saying y is 20 when x is equal to 3, and y is multiplied by 1.08 every unit. And this is where I need help. This one would be easy to get, 21.6. But then we need to multiply by 1.08 again. And we are quickly beyond what I'm able to do standing at the table. Fortunately, I have a calculator. 23.3, we'll call it. And then we'll stop at 25.2. So if I want to write an exponential function, a function for this, if I want to write an equation for this function, I can use the same structure that we did with a linear function, but instead of add the slope every unit, we're going to multiply by this multiplier every unit. So we're going to say y starts off at 20, and then we multiply by 1.08 a bunch of times. Oh, wait, x minus 3, because we started off at 3. That's no problem. We just changed x minus 3. But that x minus 3 just represents a bunch of times. Aside from filling out the table, we don't need a machine to write down a function that we want to use. We know something is increasing by 1.08, so we're just going to multiply by 1.08 a bunch of times. The pattern is repeated multiplication. We summarize repeated multiplication with an exponent. Any questions? Is that okay? Yes. Because when x is equal to 3, that's when I want to multiply by 1.08 0 times. When x is equal to 3, I have not multiplied by 1.08. And so that exponent of 0 will make the 1.08 to the 0 power, and it's 20 times 1. I want to think about where we're starting from. Is that okay? I should have gone, since this is in parentheses, probably should have gone with some single line syntax. 20 times 1.08 to the x minus 3. Any questions? This is sidebar because we're talking about linear functions, and linear functions upgrades easily exponential functions. Because we just trade our repeated addition for repeated multiplication. It has the same structure. Dang it, I can't say the first two without saying this one. Rise over run messes us up a little bit. We have all been damaged by being able to summarize the slope with rise over run. Very annoying. So let's put things at 0 to focus on this run business. So we know that the slope contains two pieces of information. The change in y, called the rise, and the change in x, called the run. Now, if we set things up in a table, we can always just say the slope, y increases by the slope every 1 unit, whenever x increases by 1. That's what's going on. Our table could look like when x is 0, y is b, and we increase by the rise over the run every 1 unit. But because it's a line, we are getting away with something here because it's a line. And the ratio of the rise to the run between any 2 points is constant. That's what makes it a line. So we could set up an alternate table where we split up the rise and the run. So we could set up a table. Oops, it's not a fraction. We could set up a table still starting off at b, and we're going to add the rise every run units. That's another way we can interpret what's going on in this equation. We could read this equation by saying y is b when x is 0, and y increases by the rise every run units. When x increases by the run. So we can start off at 0b and increase by the rise every run units. So after 1 run, we increase y by 1 rise. If we add another run, 2 run, then b is increased by 2 rise. We add the rise every run units. Everyone with me? This is still all, nothing has changed about how you operate with linear functions. I'm just trying to think about them a little bit differently because I get easily distracted by things like this. The form that we write things. The form that we write things matters. So In this case, I might want to modify the way that we write our equation. I want to say y equals b plus rise over run times x. That's thinking b plus mx says start at b and add m whenever x increases by 1, every 1 unit. But what if I want to be more, say it more with whole numbers, with integers? Y is b, and we add the rise every run units. So I'm going to add, say, plus the rise, and we're going to multiply by the number of times we're supposed to do that addition. So the way we could write this we're going to add the rise every run units. How many times are we going to add the rise? Well, you can see up here, it's going to be 1 run, 2 run, 3 run, 4 run. That's the coefficient is counting the number of runs we've done. So if we just divide by the run, x over the run is the number of times we add the rise. Mechanically, I'm just playing with multiplication. Rise times 1 over the run times x. Those three things, those three factors are just being multiplied together. So I can multiply them in whatever order I want. So let's take x, divide it by the rise first, then multiply the result by the run. Nothing up my sleeves. Multiplication is commutative. So if y is 20 when x is 0, and y decreases by 4 every 5 units, we can just write our equation. Here's our starts. Start off at 20 and decrease by 4 every 5 units. When x is equal to 5, that factor is 5 over 5 or 1. We decrease by 4 1 time. When x is equal to 10, 10 divided by 5 is 2. We decrease by 4 2 times. When x is 15, 15 divided by 5 is 3. We have decreased by 4 3 times. And so the table, hey, babe, it's not a fraction. Chill. If x is 0, y is 20. Y decreases by 4 every 5 units. Decreases by 4 every 5 units. Decreases by 4 every 5 units. Yes. No, this is going to tell us what y is depending on the value of x. So we know that y is 20 when x is 0. So if I plug 0 in here for the x, we decrease by 4 0 times and we'll be at 20. So y is 20. So the y and the x are going to be variable. This 20 is just this starting value. So we get this one fixed value and then how y is changing and how often it makes that change. The other question that goes along with this is why would you do such an insane thing? Why don't you just write minus 4/5 x? Well, in a linear function, we would, but I care about more than just linear functions. As we saw in the previous one, this whole sidebar happened because I got distracted by these friggin' exponential functions. In exponential functions, we don't get rise over run, but we still might want to have the same kind of thing. This x over run business helps when we upgrade to exponential functions. Let's say y is 20 when x is 0 and y increases by 8% every 5 units. So I have an increase by 8%, but it's not happening every unit like before. It's happening every 5 units. I want the same structure. Start off at 20, do this thing a bunch of times. Start off at 20, do this thing, multiply by 1.08 a bunch of times. That's why in with the x is where the run should be placed. And then we should simplify it by moving it under the rise. So we might not have information that says what's happening every 1 unit. In this case, x is being divided by 5, and that's at a different level in the order of operations than the exponent, 1.08 to the. So I can't just divide the 1.08 by 5. Any questions? This is one of the reasons that rise over run has made our lives difficult. It was easy and convenient at the time when all we had to worry about was linear functions. But that lack of foresight wrecked us in exponential functions. Because now, if you tell someone that something increases by 20% every 5 units, they think they can just divide it. That's 4% per unit, and it's not. It is not 4% per unit. You can't just divide those things. Look at the operations that you have to go through. I can't just take the 1.08 and divide it by 5. I could raise the 1.08 to the 1/5 to figure out what the base is, to figure out what's happening every 1 unit. But usually by the time we get to that point in our exponential function life, we're super far removed from constructing linear functions. That makes sense? Does this necessarily change anything that you do when you encounter linear and exponential functions? Absolutely not. If you've got a process in your mind that works, that's great. If you do that thing where you have like a times b to the x divided by a times b to the other x, fine. That will work. It means that you're hampering your understanding of how these functions operate, but you will get the results that you want, which is important when you're doing something like take a test. You know what I mean? I'm just trying to present another way of thinking about things. And it's just a slight modification about how we think about linear functions and then how that connects to exponential functions. Because the only difference between a linear and an exponential function is the repeated operation. Linear functions, pattern of repeated addition. Exponential functions, pattern of repeated multiplication. It's like right there. If we taught linear functions with exponential functions in mind, I really think it'd be more like this. We'd have x divided by the run, because that factor counts how often we're doing the thing. The thing being adding or multiplying. Any questions? Comment? You're paying for the calculus course, you get the algebra course for free. That's the DVD bonus material. This part gets edited out of the movie version. You know what I mean? So, I think I've explained already that I want to make a movie about math and portraying me in that movie. Actually, I want a bunch of different people portraying me, kind of like that Bob Dylan movie. They got like a whole bunch of A-list actors. We can't choose one. We want all these people to play Bob Dylan. I want that. Not that I think I rate that at all. I don't have that much ego. I mean, egomaniac aside, it's not that much. But we gotta have Dwayne "The Rock" Johnson for the icon. And then Samuel L. Jackson on the good stuff. Because that would be awesome. My math classes are rated anyway. I don't know if any of you have small children that are in school, but because We have all these different public schools. Skyline knows that we have students with children in public schools, and the public schools themselves know that those children are children of parents that are going to school. And yet, what do? We still misalign all the holidays and spring break and shit. What the ever loving heck are we doing? Can't all the public schools in an area get together and say, you know what, let's have spring break on this week so that any parents of children can have that time off together? You know what I mean? It's ridiculous. I mean, I don't mind if you have children, if you're like, oh, they have a holiday today, what am I gonna do? If you don't want to stay home for some reason, you want to drag your kids to a math class, I mean, I can't comment on the cruelty of your parenting, but if that's what you're gonna do, that's what you're gonna do. They're fully welcome here. Just realize that having small children increases the frequency at which I cuss. So, and I don't even need to see them. I'll just know that they're there because I'll start swearing a lot more. I'm like, oh, did someone bring a child today? Oh, yes. There's the little fucker. Damn it. So make sure you just bring earmuffs. Give them headphones with the noise cancellation so they don't have to listen to me swear. Any questions? Dang, I was supposed to talk about tangent lines and we didn't get to it. So that doesn't mean I'm not going to assign tangent line problems. It just means that you're going to have to attempt them without knowing what to do, which is my favorite way of introducing a topic. That's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend. Thanks for playing.
Hi, Professor Reed. Have a nice weekend.
You too.